Hello, everybody. Uh, yes, I'm Alexandru. Alex, you can call me Alex. If you want to know more about me, that's my Twitter account. I tweet way too much and I rant most of the time. That's my website, and Oriel is the company I'm working for. I'm from Bucharest, Romania. If you're ever in town, give me a buzz. We can go out for beers and stuff. Yes, so I've been working on cat's effect. I searched for an image. Literally, I searched for cat's effect, and that's the so. So cat's effect, it's a Typelevel project incubated in 2017 and graduated in 2018, and it's now integrated into FS2, Monix, HTTP4S, Adobe, and probably others. It's a foundational library that's like a sub-project of CATS, providing type classes for dealing with side effects and the reference IO implementation. And we are currently at release candidate, and we were supposed to release release candidate 2 like yesterday, but it didn't happen. So it's a little late, but it will happen like today or tomorrow or something like that. So there's a lot of cool changes in release candidate 2. It's going to be awesome. Okay, so let's go back at the beginnings. And what we had in our community in 2017. So at the beginning of 2017, Monix has had a task implementation. It still has, and it's pretty awesome. FS2 had a task implementation. Everybody else was using Scala Z 7's task implementation, which was like the de facto standard before CATS. And libraries like HTTP4S and Adobe, being the most prominent examples, had to pick one of them. So what do you do when you have multiple implementations? Well, you come up with another one. So because of my involvement in the reactive streams project, I mean my short involvement, I didn't do much but just comment on issues. I was thinking of setting up a project meant for interoperability between these data types. And but I made a proposal, but it was actually the wrong idea because it was focused on executing these data types, much like how reactive streams is structured, because my focus was on conversion between them. But eventually, you know, Daniel Spivak came up with another proposal, and what happened? Yeah, came up with another proposal with type classes that weren't as ad hoc as mine, and with a reference IO implementation, and I liked it, and I joined the project, and you know, he was right, I was wrong. So we worked on that. And okay, I'm at the Typelevel Summit. I was assuming that you all know what the IO monad is, IO data type is, but I'm going to do a short introduction anyway. So the problem with side effectful functions is that you can only execute them a specific number of times, like once, and in a very specific order. And basically, you cannot do substitution like I'm doing in this example here. So in this example, because my semaphore, let's say, is side effecting, the second example doesn't do that acquisition twice, let's say. It doesn't trigger the side effect twice. So what we say in functional programming is that this violates referential transparency. And when we describe side effects, we feel the need for an abstraction that suspends them. Well, what do you do in Scala to suspend side effects? Well, you turn plain values into thunks, and this is pretty much what an IO value is. It's a thunk that is expected to be side effectful when you eventually execute it. We say at the edge of the world. somehow, somewhere in your program, you end up executing it, but until then, it's pure. So, and I/O is referentially transparent because this works and does the right thing, and in the right order, and this substitution rule works. And I/O is about side effects, so you can do things like read lines from a file. When this read line function is executed and returned, it's not going to trigger the side effects immediately. It's not going to start opening the file handle and then reading from the file. It's going to wait until later, but you can still take the result and compose it with something else and trigger have another value in return. So, and compared with the old I/O data type in Scala Z, this I/O is capable of side effects, of asynchronous, describing asynchronous processes. It's more equivalent to the old task in Scala Z7 and to the task in Monix. So this is a sample that describes something that happens asynchronously. This would be something like the equivalent of future apply, where you give it a thunk and it's going to get executed on some other thread managed by some execution context that you're passing in there. And it's the definition of the async builder is basically the definition of asynchrony. You're basically giving a callback that you register to some process that is supposed to call that callback with the final result when it eventually finishes, and you know you can describe pretty much with it everything with it. So, speaking of which, now in Cat's effect, you no longer need to pass execution context around necessarily, because we've got a new timer, which is like it's supposed to be like a pure execution context that's given to you by the environment. And you can simply do thread shift with it. And in this case, we are simply saying that we are describing what we described on that other slide, execute this I/O on some other thread, not on the current one. So the definition of I/O, as we've said in the Scala documentation, is that it's a pure abstraction representing the intention to perform a side effect. It's not executing it yet when you receive an I/O. It's just an intention, and you can work with that. It's a description. And for the impure developers amongst us, and I'm one of them, a good way to form a mental model about what I/O is basically a thunk that returns a future. That's not actually true, but that's just for having some mental model about what it is. You're working with basically functions when you're working with I/O. So the original philosophy of the project is that Cat's effect is about capturing effects. The I/Os described are doing atomic evaluation, meaning either all of it executes or none of it at all. It doesn't deal with concurrency or race conditions or cancellation at all. Type classes meant for abstracting side-over effects are provided in order to leave the room open to other implementations like Monix's task, which is more sophisticated. And in doing so, it avoids a Scala Z7 task situation where everybody knew that it had certain problems, but nobody could replace it with something else because the community simply used that without abstracting it with a bunch of type classes. So just as a reference, Monix task has been cancelable since 2016. When I released it, well, it took several months before I actually got a version that was usable. but due to the bad experience with the cancellation mechanism that was pretty ad hoc in Scala Z7, people didn't like it at first, let's say. But it's now, the design in it has proven to be useful, and it's pretty much integrated at this point in Scala, in cat effect. And another thing that happened is that in August 2017, John DeGoes announces, okay, Scala Z8 is going to have its own I/O implementation and it's going to be cancelable. And it convinced everybody that it's a good thing. So I'm eternally grateful to him because I believe in having a cancelable I/O. Plus, we borrowed about 2 ideas from them. Maybe I'll mention them later. And competition is good, in my opinion. So now we are competing, and I've been in competition mode on, yeah. Basically, I started optimizing the implementation, importing the things I did in Monix's task, and then I finally provided a solution for cancelable tasks, for cancelable IOs. That's inspired by Monix, but we'll talk about it later. So there is like this guy on Twitter that posts funny pics, and I'd like to know who he is. I mean, I like to meet him because he's doing an awesome job with this. Are you sure you want to cancel this? Oh, yes. But the reason for why I prefer cancelable stuff is that back in the day, when I was working on this web service that had insane amounts of traffic, we also had strict latency requirements from the partners we were integrated with. So we had to reply in 100 milliseconds, which included the network round trip and so on. So we had timeouts on our tasks that were doing requests to our internal web services. And I pretty much went ahead and described it naively with something like this. And I was pretty proud of myself because I was describing a delay that would delay some future, and then I would describe a timeout operation based on that delay. And I was so pleased with myself because I described two functions that I thought they are reusable. Well, they aren't reusable because my futures were leaking the timeouts. They were leaking the timeout runnable scheduled in the scheduler. And I mean, we were getting like 10,000 requests per second, and I was creating 10,000 runnables in the scheduler that were never canceled. And I mean, most of those tasks were fine. They didn't need to be timed out and so on. So the same server simply crashed. That was the naive solution. So don't do that. I mean, Future has first completed of. It's used for race conditions, but whenever you have a race condition with Future or some other abstractions that are not cancelable, basically they don't work. It's like an accident waiting to happen. So what I ended up doing is something that's less composable, a function that pretty much is tied to the internals of the scheduler, and it uses a promise and creates that race condition, and it checks out, okay, on completion, cancel that task by triggering the cancellation token returned by the scheduler, and then in this way it doesn't leak. I can no longer split this function in two. It's no longer something that I can reuse, this concept of triggering something later. But it's a race condition that I created that's usable for canceling the timeout operations. It's not really, it doesn't really solve the whole problem because the request itself cannot be canceled. I mean, maybe you are doing web requests, and by not canceling, we are not closing the network sockets in time. And then you've got a file handle leak, which also happens to me. So that's not the way to do it. Whenever you have to deal with race conditions, if you don't have a cancellation model, you're basically screwed. So the naive way to do it with the I/O implementation that we had was to basically use the async builder, schedule that, and so on. But there's no cancellation token that you can use anywhere inside that. So what people did, and this is I'm talking about right now, for example, of FS2, which has a cancellation model in their stream. What they used to do was to create actions that would return a tuple of two things, like an I/O linked to a shared mutable state that represents basically a promise that's going to complete at some point eventually with the result, and another token that can be used as a cancellation token. Notice how I implemented this. So internally, everything is suspended in I/O. Of course, no side effects are being triggered immediately. But I used an internal promise. Promise represents a shared mutable state. I'm then completing that promise in the scheduled runnable that I'm pushing in the thread pool. And I'm then creating a cancellation token that's linked to that promise, that's linked to the token that's what's returned by the thread pool, and then I'm returning both. So I'm creating an indirection. Both are modifying the same shared mutable state. We have to modify the shared mutable state because we need memoization. I mean, even if you're receiving an I/O, you can only cancel it once. I mean, they need to be linked somehow. So the action of the inner I/O that you're receiving has to be idempotent, let's say. So it's complicated. It's complicated working like this, plus these cancellation tokens end up infecting your whole code base. Once you have it returned by an action, you have to return it in a composition of multiple actions that all of them could be cancelable, so you have to make a composition of all of them. So it's something that can become really difficult to work with. Also, I use a tuple. Well, we could create a type alias and call it a fiber and have a join and a cancel, and then we could call that a fiber for what is essentially a tuple of a join and a cancel, right? Like I did back then. And then we could implement a cancellation model in I/O instead, which is now the cancelable builder, and the cancelable builder works like a sink, but instead of returning unit, we are returning a cancelable token that then can be used later in whatever compositions we are doing in race conditions, right? So it's effectively the same thing, except that the cancellation token is different, is hidden, it's implicit in that I/O. And now it becomes really easy to define a timeout operation. Again, I'm tying myself to the timer that we defined because it's easier to work like that. Sleep. The sleep operation is something that's cancelable. We can, after a sleep, we can trigger an error that's being raised, the timeout exception, and then we can create a race between them. This time it's a safe race, and then we can like stream the result. In case the timeout succeeds first, then our source gets cancelled, or vice versa. So we no longer have a leak here. And the realization in this case is that basically what I just described is, oh my God, I'm really bad at timing. So what I just described is the start operation that gives you a fiber, which is basically a tuple of a start and a join, and then you can basically take any task and transform it into one that can give you a tuple of the result and the cancellation token. So cancellation is basically the ability to do this, right? Given a task, you can basically get its cancellation tokens such that you can cancel it in race conditions. So cancelability is nothing more than the ability to carry the cancellation token around to use it in race condition. That's a code by myself. So the API. We have got multiple type classes that can be used to abstract over all of this stuff. New are concurrent and concurrent effect. Concurrent basically has race and the cancelable builder. Async and sync and effect are the old type classes, and they are still useful to describe non-cancelable data types. We have a bracket right now. This one, I was convinced by the Scala Z8 that we need. That can describe, basically try with resources from Java, but in a safer way, in something that works with asynchronous processes as well. Bracket can be used to release resources in case of error or in case of cancellation. It works, whatever happens to that use task. We can easily describe an operation like this, like read lines from a file, like this is the query part, this is the use part, this is the release part, the release that can happen in whatever condition. This would be the concurrent type class. We've got and I encourage you to read the documentation because it's really interesting. We've got the cancelable builder that I just described. We've got a way to transform tasks back into atomic units that can be executed either all at once or none at all. Because the reverse of doing something cancelable is also useful. On cancel raise error to materialize cancellation. In case cancellation happens, the task ends up ending in an error because by default tasks don't do that. By default, cancellation yields non-terminating tasks. And start that you just saw and raise pair, which creates race conditions between tasks, and you can use that to cancel the other one, or you can actually use its result somewhere else. A bracket can be implemented in terms of on cancel raise error, and it can give us with on cancel raise error we can throw a special error that we know about, and then we can differentiate between the cases. This was a successful branch, this was a cancellation, and this was an error, and then trigger responses based on that. And some interesting use cases I'd like to show you about, and that we maybe some features we introduced lately. We've got timer, which is the pure scheduler that can schedule timeouts, things to happen with delays. And the cool thing about it is that you cannot describe a sleep with this signature if it's not cancelable, it's not safe doing anything else. We've got a timeout operation on never, so you can time out any task and do cancellation. Not going to talk about this one. Everything in Cat's effect is very explicit, so in case you want to make like a long loop to be cancelable, you can introduce IO cancel boundaries in it, meaning that whenever it hits that boundary and it observes that a cancellation has occurred because it has like this internal boolean that switches to true, then the processing simply stops. Such a loop wouldn't be cancelable by default. We have like an mvar now in release candidate 2 that I imported from Monix. We also have a ref that is imported from FS2 and Semaphore, and a lot of IO apps that I'll talk about it in a moment. So with mvar, you can basically describe a lock. Well, if you're going to end up timing out something that acquires and then uses a lock, then you can end up with a deadlock. So the lock itself, mvar, is cancelable. You can yield cancelable tasks. We also have a semaphore that you can use as a lock. This is just an example of using mvar. The semaphore itself is cancelable because otherwise, in a race condition, again, you can end up with a deadlock if the yielded task isn't cancelable. So This would be the semaphore usage, which is, again, in release candidate 2. And something really cool that's like a really recent addition, like 2 days ago. We've got an I/O app that you can use to describe what is a main function for your program that returns a main. And the really cool thing about it is that it hooks to I/O's cancellation mechanisms. And in case you're pressing Control-C or you're sending the application a SIG term or a SIG abort, it's going to trigger the I/O's cancellation. So it hooks into the shutdown hooks of the JVM. And this is something useful in a web server as well, because if the client forcefully closes the connection, you don't want to keep processing that request, for example. Maybe this is something that will soon be available in HTTP4S. Anyway, so a couple of really quick design choices. I/O is not and will not be as sophisticated as Monix's task because its simplicity is a real virtue, in my opinion. I/O is explicit by design, so whenever you need asynchronous boundaries, you have to specify explicitly I/O shift. Whenever you have a loop that you want cancelable, you have to explicitly specify cancel boundary. And there is some separation of concerns there, sync versus async versus concurrent. This works with really well with parametric polymorphism because you can keep adding restrictions as you go when in abstractions that make use of those type classes. And it doesn't do auto-cancellation, and this is the current debate that we are doing with the Scala Z folks. And plus Monix's task can do auto-cancellation if you opt in, but auto-cancellation breaks the laws of these type classes. And I believe that the default should not be auto-cancellation because this simplifies everything. And if you have auto-cancellation, it basically infects your host type class hierarchy. A restriction on a monad is no longer just a restriction on a monad. You have to ensure that the flat maps are working. So coming soon, ref, which wraps an atomic reference in something pure. Deferred, which is a pure promise. These were imported from FS2. Semaphore also imported from FS2, which is like a pure semaphore you can use to limit concurrency with those asynchronous tasks you have. And var, which is a really cool abstraction imported from Haskell and I/O app. So yeah, I'm really bad with timing. Sorry about that. Yeah.
Any questions?
Yeah, will the new version of Monix have a stream parameterized over effect type?
Observable, no, because observable doesn't need an effect type. Observable itself could be an effect type. But iterant, yes. So a big motivation of mine to work on Cat's effect was to work on iterant, which is like a pool-based streaming approach that is parameterized over the effect type. Mm-hmm.
More questions?
So in what case do you recommend using task, or in what case do you recommend using I/O?
Task is more sophisticated, so when it comes to concurrency, there's always this tension between having throughput or a good mental model about what's going on versus having fairness. So if you've got a lot of tasks running in parallel, Monix's task can be more useful because it does stuff like processing stuff in batching and leaving the other tasks running concurrently a chance to execute. Or it has, for example, task local, which is kind of hard to implement, and I barely got it right, which is like a thread local for tasks. It basically has a scheduler that gets injected everywhere within its internals, so it can do like some smart stuff with it. But the cool thing about I/O, because it's simpler, you can basically understand how it works. So that's why I don't have a problem with it being exposed in the effect type class, because there you've got a guarantee about its execution model, let's say. This is another debate we are having right now. The GitHub channel is fun, by the way. So yeah.